the Internet, ubiquitous wireless communications, automatic control systems. These are all familiar aspects of our everyday lives here on Earth. Over the last decade, these and other technological advances have enhanced the way we live. For remote human and robotic exploration, wireless and network technologies can be further exploited and enhanced for increased automation, awareness, and probability of mission success. The new network technology, called Disruption Tolerant Networking, or DTN, is of particular interest for space exploration.
3, 2, and away. It's released and on its way.
Network communication initiated.
NASA's Space Communications and Navigation Team is partnering with Vint Cerf, co-inventor of the TCP/IP protocol, JPL Distinguished Scientist, and Vice President at Google, to develop, mature, and accelerate the infusion of DTN into space communication networks.
The delay and disruption tolerant networking protocol environment allows for a much broader range of applications to be supported, ranging from the kind of low delay, very rapid interaction that we get on planet Earth to the interplanetary uncertain delay, uncertain disruption. It works across all of those regimes, so it's a much richer system than the one we've ever had before.
The collaborative effort supports a series of tests that will evaluate DTN-enabled systems for use in space and also facilitate their application in terrestrial networks. At Johnson Space Center, NASA's scientists and engineers are evaluating DTN technology over wireless communication and sensor networks and are evolving the technology to support future robotic and human missions.
All networks now online.
One scenario in which DTN will enhance the safety and situational awareness during operations is tracking of a rover, robot, or astronauts. For this test, crew members leave the habitat to simulate a simple trek across the terrain. Crew members back at the habitat and the operations team at the Mission Control Center monitor the vehicle as it moves through the terrain. Navigation data is transmitted from the vehicle to the habitat over an 802.16 wireless network. During this scenario, the vehicle is seen moving behind a large object, and suddenly a loss of signal occurs between the habitat and the rover. During this time, the DTN node located on the rover continues to store data during the outage. Once the vehicle moves from behind the object, the link to the local network is restored. The DTN node begins to transmit both new data as well as stored data back to the habitat. Crew members are now able to see the position track updated on the display, where the trajectory pertaining to stored data is shown as a different color.
3, 2, 1. Tracking initiated.
With the growth of available data afforded by radio frequency identification, or RFID, and wireless sensor networks, systems must be able to accommodate a continual, event-driven flow of data in an automated fashion. Current techniques require labor-intensive, ground-based scheduling. DTN can significantly improve network performance and efficiency. Future systems must allow for seamless merging of mobile networks. For example, DTN, in conjunction with advanced middleware technology called BioNet, will enable automatic tracking of RFID-tagged inventory transferred between mobile environments. As the Lunar Electric Rover approaches the habitat, 802.11 wireless networks merge when in range. As the crew leaves the rover, they remove 2 cargo transfer bags, or CTBs. As the crew moves away from the vehicle, items are removed from the rover inventory database. As the crew enters the habitat, items passing through the RFID portal are identified and the habitat monitor shows inventory increasing. At the same time, ground consoles automatically receive updates.
The Dtn project is a NASA agency project, and as part of that we've set up something called the Dtn Experimental Network. This essentially is several nodes at each center that are interconnected. There are Dtn nodes at each center, and it's essentially a test bed that the agency uses for testing out different Dtn applications at different scenarios. And we use it to isolate problems with the Dtn technology, then we work on fixes and come back and try and test them again and see if they've been corrected or not. And it just allows, it's a great way to get all the centers and all the smart minds together to do some investigative work and some engineering work to improve the Dtn protocol.
Dtn technology will allow local and remote databases to be synchronized automatically as RFID-tagged inventory is stored, relocated, utilized, or discarded. Within an environment such as a habitat, even if the synchronization is interrupted by a network outage, no data will be lost, and synchronization will resume when connectivity is restored. Smart Shelf, RFID soft stowage, and RFID recycle bin technologies enable automated inventory tracking and localization.
For a lot of mobile applications where connectivity is often unreliable, Dtn will be a very powerful adjunct to today's traditional world. In addition to that, sensor networks can also make use of this protocol because in a sensor environment you may or may not have the connectivity that you need. Sometimes you have to be very quiet while you're waiting for the sun to come out so you can recharge your battery, so that means the link that you would have provided isn't available. Mesh connectivity and store and forward operation is a natural with the Dtn architecture. So I'm anticipating a lot of terrestrial applications involving sensing and involving mobile operation.
Other Dtn-derived benefits include the efficient and reliable delivery of critical data. For example, biomedical telemetry that must reach a ground-based flight surgeon for diagnosis. Here, engineers are testing this scenario by transferring heart rate telemetry during a communication outage. The engineer looks at the inventory monitor and can see which RFID soft stowage cell the monitor is in, but not the exact CTB. The engineer is able to quickly identify which CTB the monitor is in by using a handheld scanner. If the network link is available, the data will automatically transfer to the flight surgeon on the ground. If the link is out, the data will be stored and automatically transferred by the Dtn when the link is reestablished. Without Dtn and advanced middleware, ground controllers would be required to determine the correct time span of data and build commands to retrieve it. When the flight surgeon completes diagnosis and prescribes medicine, it can be quickly located.
What excites me most about wireless technology is that it's always changing. There's always a new problem to solve, and wireless technology provides answers for a lot of questions, but new questions keep coming up, and they're pushing for bigger and better applications, and just the fact that wireless technology is always changing means there's always work to be done. It just allows us to keep busy and keep doing what we do.